Good day, everybody, to all the attendees. My name is Christian Mont. I'm Sales Director of IPCOS, and welcome to this webinar on AptiTune. After the successful webinar in March on the concepts of AptiTune, we received several questions from the attendees to have a dedicated demo on the tool itself. So we selected a real-life case from an NGL plant in the Middle East to show the power of AptiTune. The presenter of today is the IPCOS APC engineer Michiel Huizer from the Bokstel office in the Netherlands. Michiel has worked on many plants around the world on APC projects, but also on base layer optimization using AptiTune. Besides that, he is also an AptiTune trainer, so he's very well placed to present the webinar of today. Questions can be raised using the chat box to the right of your screen. We will collect all the questions that you raised during the presentation and the demo. So, and at the end of the demo, we will switch to the questions and answer session. So please do not hesitate to raise them already during the presentation. I will collect them, and at the end, I will come back to you, and then Michiel can answer the questions. So I hope you enjoyed this very informative webinar. I will come back to you, let's say, in about 35 to 40 minutes. So Michiel, the virtual floor is yours.
Thank you, Christian. So welcome to the webinar from my side as well. So what we're going to do today is we'll have a short introduction of the example, or just a brief going through the plan and showing the two loops we are going to tune. Then we'll move on to the live demonstration and we'll show some results. So if we look at the schematic of the plant, which is simplified, of course, we see here the gas coming from the well, and this is the main choke valve controlling the total feed flow to the plant. Then we move to some scrubbers and separators, and we go to the cold section and export system, and there we have a pressure controller located just before the expander, and this pressure is controlled by means of the expander feed. Then going further into the plant, we will have the liquefied NPL coming to the demethanizer system, and in the demethanizer column, there is a tray level controller, which we'll look at first. So we'll look at two loops. We will look at this tray level controller, and we look at two interacting loops, the pressure and the flow loop, controlling the total flow of the plant. So for the live demonstration, I will move to AptiTune now. So imagine we already did a step test. So we already generated the open loop data needed to make our model. And I'm going to start with importing this data into AptiTune. Now there are several options of importing data into AptiTune. One nice feature as well is the OPC import wizard, which allows you to connect to your DCS and record the data as you do the step test. Now for this demo, we are using the INCA import wizard, and we are going to import the data which was saved to text file. So you see I started the import wizard, and it's just a welcome screen, so I'll skip ahead. Now there are several different options of importing data. I'm going to use text files in this demo, but you also have the opportunity to import text files, DMC collect files, or INCA test files. So there are several options. So for now, I'll select the text files. Now in this text screen, we have to select the files that we use to import the data. It can be that there's more data signals located in one file, or as I have now, I only have two files, so each signal has its own file. So I select both files, and you see them appearing here. I can press next. Now in this next section, we have to select which is the separator, separating the timestamps from the data. And we are choosing here a top because it's separated by a top. So now you see two data columns separated, and you can press next. Now in this next screen, we can select which is the header and which is the data, which lines are header files or header lines and which are data lines. So the signal name is located in the first line, so I'll say header row 1 is my signal name. Then the description is located in the second line, so I will select line 2. Engineering unit is located in the third line. So I will select the third line. Now the data is not starting in the fourth line, but it's starting in the fifth line. So I will select the fifth line, and I can move ahead with my import. As you see here, this is to recognize the timestamp. Now the timestamp column is column 1, and it recognized already the time format here. So I'm ready. We could select a different time zone, or we could also generate the timestamp ourselves. But in this case, I will just do the default. Now here we could select more or one column if the file contains more than one column. So more than one signal we could choose not to import that one. But in this case, I will import everything. So the last screen is about the sampling time, which I will leave to automatically determine. And the number of interpolation samples I leave as well to 10. If this is the amount of gap you allow for the data to become bad. So if gaps in the data are larger than 10 samples, they will become bad. If they're smaller than that, it will interpolate and more or less fix the gap for you. Okay, so everything is imported successfully, and I'll press finish. So now these two signals appear in AptiTune under the signal, in the tree or under signals. So I can select both of them and make a plot of them. Now the different ways of manipulating the data you see using the trend, but I will go for a distributed scale, and I will fit the data like this. So this is our level loop, and as you can see in the red we have the output of the controller, and in blue we have the measurement. Now, I recorded this data, and this data contains closed loop and open loop behavior. So to get my modeling correct, I need the open loop data only, and I'm going to select the open loop data by making the other data bad. I'll go to this point here, make this bad. Now it's asking both signals, which is okay. And I'll make everything so like this. So now I've selected the identification data, which is now still in showing in white. Now in this case, it's maybe not convenient, but it can happen that there are many signals, or you did that for more than one loop. You have the opportunity to save the signal list, and I will do this and save it under LIC 1, 2, 3. And so I can reopen this plot if I wanted to. It's located here in signal list. So you can organize your data a bit better by using signal list. I will close this for now. Now one thing we have to do is we have to build our model. And we build our model by using a case. So I will add one new case. Here I will just call it case because we only have one. Now first I have to select my independent, or I have to select my inputs, and I can select the signals by dragging them on this pane. So now for independence, I have selected the output of the controller. Now for my dependence or my output, I will select the measurement, of course. Now because this is a RAM, I have to tell AptiTune this is a RAM signal, so I will make this RAM true in this case. Okay, so now we have selected the input and the output. Of course, if this was a MIMO case I was showing, I would have selected more than one output and more than one input. Or if you want to have some, let's say, disturbance input to improve your model, you could choose them as well. But for now, we only have one input, one output. Now I'm going to build a model, and I'm going to choose here to add a new trial, so building the model. I'm choosing 120 PID parameters, sampling time is 1 second, smoothing factor I leave to default, and I will only use a PID model for this example. Now we have added that, and as you can see, the case is showing up in red. That means that it has changes, pending changes that have not been run yet, and I can run this case. Now it's directly showing me the two models I am getting. So I will get an unconstrained and a constrained model, as shown here in the case. Now the unconstrained model is just a pure algorithm, let's say the pure PID algorithm getting the unsmoothed model, and the constrained model has used smoothing. So this is the default. I can add even more constraints. So let's say if I wanted to fix the dead time here, I can use and select the constrained model and fix my dead time here, and as well I can fix steady state behavior on this side. So now I am enforcing some dead time, and I'm enforcing the time to steady state. So now it's turned up red again, and I have to run it. So after doing this, you see the model has changed slightly, and as a nice straight line from this moment, 1.3 minutes, and it had a dead time of 0.2 minutes. So now, if I can judge if I'm happy with this model, I can go to that model and say show prediction. And now it's showing me the real data, as well as, let's say, the simulated signal for these steps. And the simulated signal is in red. As you can see, we have a reasonable fit. Some disturbances coming in here and changing and not fitting exactly, but all in all, a nice fit, I think. So here you can judge your model. This works also for MIMO models and all the modeling you can do. So this is really where you judge if my model good enough. So after you have decided that you're happy with your modeling, you can move on to the step to the three parts which says model matrices. And in the model matrices, you can build your model together. So in this case, I only have one, let's say, model only from one input to one output. In a MIMO case, I would have more models, and I could have used the models from different cases to build me one model matrix. Well, I will create a new model matrix, and I call it level. And I will open up these levels. As you can see, this is an MTV matrix, and I can drag in now my constraint model, and it will ask me if I want to add the curves, and I do want that. So now you see that I have constructed a model matrix which we can use for our tuning case. Just to skip ahead a bit, the Nemo case would look like this. It would be the feed expander model. So we'll focus on that one a bit later on. So for now, I will add a new tuning case, and I will choose my original model. And as you can see, I have to choose here also a DCS manufacturer. Now in this case, I will choose a Yokogawa, but you have the choice of using a different one. I will add this case, just close up these views and open up this case. Okay, so this is the main screen of the tuning case. As you can see, here are the tags that are related to this loop. It says if it's a direct acting or reverse acting, and you have to set the ranges. Now in this case, the ranges are 0 to 100% because it's the level the operating range is a valve. So it's also 0 to 100%, but this could be different. And here on the side, we can choose which mode the PID block is in. And in this case, the mode was I on error and P on measurement. So I'll leave that. Just to compare the new tuning, let's say, with the old one, I will add here in the existing tab, the existing controller, which has a P-band or P-band of 350. Of 70. So now I set the ranges, I have set the existing tuning, I set the mode, and I can run the case. Now if I run the case, it will first show me the default tuning here. And it will show me the step response of the closed loop system. So this would be, let's say, a default tuning which you, if you are happy with this step response, you can already use online in your on your DCS. So let's say this is the quick method, which gives a nice result. But I want to show the more advanced features of AptiTune, so I will go and change some things. I will increase the simulation time a bit to make the plots more clear, and I will uncheck this Nicholson method, which I will come back later to that feature. Now, if you can see, I have still checked here the gain margin and the dead time margin, which are my stability constraints, and I will run this controller now. So I get a slightly different controller. It's a bit faster, and here you can see the step response. Another thing you can see from the closed loop behavior is how the controller behaves to a load step. And here you see how the controller behaves to a load step. So in red, it's the measurement, and in blue you have your OP. So this is how it will respond to a load step. Now, a very important thing here is the robustness plot. You have to make a judgment how robust is my controller. And in this case, you see here the overview of the robustness plot. Now in the center, in the red area, is the current model, let's say. So this will, if I click here in the screen, this will depict our current model, the model we have estimated, and we think it's the correct model to this plan. So if I click somewhere else in the screen, I will change, let's say, the gain. Let's go up. I will change the gain of the model. I've seen on the side, you see here the original model and the modified model. And also you will see the closed block behavior on the set point step for this new model. And also how it reacts to a load step. So you can make a judgment here, how will my controller perform if my plans will change a bit, if my gain will change, or if my delay will change. Another thing you will see here in this robustness plot is the blue line, which is actually our gain and that time constraint that we have set here, which is the 3 and the 2 here. Also visible in this plot is a purple line, which is the stability line. So if I go above my purple line, so if my gain at that time would be the same and my gain would be 6 times bigger, I would have an unstable control. Okay, so this is all to judge the closed loop behavior and if you're happy with that. I will close that for now and save this controller as robust. Now, just to show the effect, I will uncheck the gain margin and uncheck the dead time margin constraint, and I will run it again. And you see that the controller is much faster, and the movement of the OP is also much more aggressive. Now, if I look at my robustness plot now, I see that my stability line is actually going through the red area. So AptiTune is indicating here that you are actually tuning the controller faster than it's advised. And you have to be very sure about your model to leave tuning like this on DPS. Okay, so I will just lock this controller as fast. Okay, so now I'll check the gain margin again. And I will check the Nicholson method again. I will run this as the last example, and then I will compare all 3 of them. So if you save controllers like I did, you can lock the controllers and you can compare different results that you have obtained. So if I go to the log overview, I now have my current tuning, my fast, and my robust controller. And I can see the step responses of all 3. Now clear is that the fast controller is much faster, the robust controller has a bit overshoot and is considerably slower, and the controller using Nicholson method is much more slow. And the real difference between, let's say, the robust controller and the Nicholson controller is that it removes the oscillations. So this picture is normally checked if you are tuning a level, and it will make sure that if you have a response to a load, as I'm showing now, how will the controller perform. You see that the fast controller has a lot of oscillation still in there. Our robust controller also has an oscillation or 2, and our let's say soft controller has no oscillation. Okay. So now we'll move on to the new case. So I will again add a new tuning case. I will go to Nemo. Now I will use the feed extender model, and I will select Yokogawa again. Maybe first just go briefly to that model. Now this is the two interacting loops in the Nemo case. We have the total flow going to the plant. If the flow increases, or if the valve position increases, also the flow will increase. The valve position increases, then also the pressure will build up in front of the expander. Now if we increase the speed of the expander, the flow will go up and the pressure will go down. So these two loops are clearly interacting with each other. Now I'll go back to my tuning case Mimi, which should be Mimo. Okay, so for this one I will choose the Yokogawa PI for the first loop. And in this case the range is not anymore 0 to 100, but I have to set it to 0 to 1400. The existing tuning in this case is a P-band of 100 and I have 50. Now for the second loop, my P-value range is 0 to 1500. I also have a PI control in PI mode, and I have 50 and 100 as existing tuning. So this is just the same the last time, and I will run fine tune now. Now as you can see, now the view looks a bit different. So in the diagonal we have the two controllers. So the pairing of the controllers are on the diagonal. And on the off diagonals you will see the interacting effect of a step on one of the two controllers. So if we take the flow as an example, here we see the response of the flow to a set point change, and in this plot horizontally to the right you will see the pressure reacting to that. So also in the Nemo case we can look how these controllers respond to a load change, which you can judge here. And of course also we have for the diagonal, so for the both of the controllers we have our robustness plots, which we can judge how robust we have tuned these controllers. So this is all the same as a CISO case, only in Nemo, and you have to make the same judgment here. And now we will move to, let's say, the advanced options. So, as said before, you can add a lot of constraints in the tuning, and all constraints will make the controller slower, as well as the advanced options, which will all make the controller slower. If we look at the step response again, I see that we have quite a bit of overshoot here on this pressure loop, which maybe I don't like. And we can change that by selecting loop 2 and making the maximum overshoot 2%. Now if I run the controller again, you will see that I have a maximum overshoot of 2%. So this constraint has slowed down my controller, but has met my, let's say, engineering demands of 2%. I will log this one as overshoot. Let's go back one step. This is my original tuning again, let's say the default tuning. Another thing we can look at is how is noise amplified and how is noise moving the output of our controller. Now, as you see here, we have quite a bit of movement due to noise. on the pressure controller again. So then I can use one of the advanced features here and set an OP noise limit. We'll choose an OP noise limit here or 0.1, and I will run it again. Now this would be the step response of the closed loop system, but I'm now interested in the response to noise, and you see that the noise on the OP is greatly reduced by using this constraint. So this is how you can use AptiTune and the constraints in AptiTune to change your controller from an engineering perspective and making engineering specifications in there. Just as a comparison, as a final thing, we see the existing tuning, current tuning, and our overshoot tuning. So here we see our three controllers we have looked at. We have our overshoot, which is almost the same as the existing tuning is quite slow, which is in blue. And we have our overshoot tuning, which is in red. You see that the flow is a bit faster and the pressure is a bit slower. And then we have here our noise tuning. Also here you can make different comparisons. And if we look at the noise level, then the current tuning, we see clearly that the overshoot tuning is a bit more aggressive. And if you compare it in this plot here for the pressure loop, you see that the movement of the OP due to noise is reduced in the current tuning, which was the tuning that had the OPC or the OP noise limit. So I think this is what I want to show for today, and I'll leave to Christian to go over some questions.
Okay, thank you very much, Michiel. So now there is time for questions and answers. So you have your chat box on the right of the WebEx screen where you can type in all your questions, but in the meantime already several came in. So we will start with these ones. A very practical one, I think, from somebody who does day-to-day tuning. How can you compare your existing tuning with what comes out of AptiTune?
Okay, yeah, so let me just go back a bit. That's why I filled in the existing tuning. Let me take the FIFA loop. So you have here in your log overview, you have your existing tuning and let's say our robust tuning. If I can judge the differences by looking at it. So in the original tuning, you have quite a bit of oscillation, and here you have in our default tuning a nice step or a better behavior. Let me put it that way.
So you can just type in the existing.
Yeah, you can, and this has two purposes, because if you type in the existing, of course, you know still what the existing tuning was, and you can make comparison as you go along and log during your project, during your tuning, you can log different controllers to how they react and keep track of what's happening.
Okay. Another very practical question coming from the Emirates teams. What can be done with cascade loops?
Well, cascade loops, we have to tune that in two steps, so there's no built-in support for that. We first have to tune, let's say, the state controller and make that as fast as possible, and then do a step test on the slave and tune the master. Okay. So it's a two-step method. There are some plans to support this within AptiTune.
In a more automatic way.
In a more automatic way.
Good. Yeah. Then something which is really linked to MIMO. Does that system give, let's say, advice on pairing, which means that which PID controller should control what? So this one a temperature, the other one a pressure, and if you change that, perhaps then it's not that good. So what does this AptiTune does regarding to advice on pairing?
But it doesn't give you direct advice on pairing, but it does give you advice if you've done it badly. So if you see this model, the pairing is automatically on the diagonal, and if I would change that pairing, I would get warnings that it can be badly paired. So there's no advice in this case. I can't show you that. So it's only advice if you done it badly.
Okay. Yeah.
Of course, that's still an engineering choice.
Good. Then, so there is a question of somebody who asked, can you explain again why case became highlighted in red while building the model?
Okay, so if I apply any change to the case, so doesn't matter what I do, I'll just close this a bit, then it will show up red because I've made a change. So if I add something, you see that this new thing I have added is showing up red, meaning that I need to rerun the case.
And then it ripples through the model, the tuning.
Yeah, then it ripples through the model. There's one, but if you have updated a case and you have built your model matrix, if you want to actually update the model from that case, you have to make that. That's your choice to do that, whether you want to do that or not. So you have to press update
manually.
Here. Yeah.
Mm-hmm.
Yeah.
Okay. Then the question which was raised very early during the webinar, because it's about getting data. Is there a way to get historical data in? So what are the different ways to get historical data in AptiTune from historical databases? Or how does that work? What is possible? What is not possible?
Well, yeah, you can import with all different kinds of, let's say, text files or other formats. That's the way to get historical data. So you have to export it from your DCS or your historian and import it by means of, let's say I did it by means of a text file.
That's the text file, but you support more formats, let's say.
Yes.
Okay, good. Now, assume, because you talk about Nemo, and then you have already made your model, because you did it with for APC also. So can you use then these models? So can you import then already the model? So okay, you have done the step testing, you have done the data capture, and now you just say, okay, I even have done my modeling. So how can I use these models in AptiTune? Can I already start from a model? Can I import the model?
Yeah, we support different models. As I did here, I imported this model from actually our discovery programs, our own program, which is also a modeling tool. You can import models from there. You can also import models from the AptiTune product. Okay. So there are different options there.
So then you can already start from a model which you want to build
if you
third-party tool.
Yeah.
Good. A very detailed one. How can I use a measurement of a disturbance signal to improve the model? You said that it's possible, but how?
Yeah, well, let's say I have a disturbance signal, let's say outside temperature or something I can measure, but I can't influence, which is actually influencing my model in my step test. And I can use that information, extra bit of information to improve my modeling, and I will get let's say a model from something I can't influence. But this is maybe a bit to search for a scenario.
But then you have a model with two inputs and one output.
Yeah.
And you only look at.
And I only use then the one from the input I can influence to the output that is used.
Okay. Another thing is nonlinearity. So how can you deal with nonlinearities? And then valves seems to be a very good example. So CV curves of valves which are far from linear.
Yeah. So if you step to a big range of the valve, you can see nonlinear effect, and you can use it. You can, let's say, account for that in several ways. One is you can use a transform to get a nicer linear model. So then you know what is your transformation, so what is your fixed nonlinear behavior, and what is your linear model. And then you can use this information actually in a robustness plot on one side to say, okay, I'm stepping through a quite broad range, so I have to have a more robust controller dealing with gain changes. yeah, so that's the main thing you can do, or you can use the transformation in a DCS if you have that possibility.
Yeah. Does AptiTune generate reports?
Yeah.
So you can compare things, it seems, but
yeah, you can generate a report of the tuning case just for your own and you can use that for your own administration or what you done. So it looks like this. You have a tuning case, you have some of the responses, the model in there, and the tuning in there. Get briefly to that, but yeah. So there's a possibility to make a report of that.
Okay. Then a more commercial administrative question: can we get a trial license? That's the one I can answer. So yes, you can. Yeah, of course. So if you want to have a trial license, which will mean that you have a full functional license, not only one which runs some pre-defined projects, but it's a fully functional license, but of course which is limited in time. So you can contact me. But I will anyway, at the end of the webinar, send around an email with some more information about a link to where we have recorded the webinar and so on. So, and then you will also have my email address, and then you can ask for a trial license. Good. Back to techniques. Then, yes, the word closed loop pops up here on the chat box.
Yeah. So. As said before, I've used open loop data to make the modeling, and you have to do that in AptiTune. We find that using the open loop data will get you much better modeling than using closed loop, and that's not possible in that sense to use that and make a model. So that's very important to remember that you have to do an open loop test.
Okay. One more here, performance monitoring. So can you also use this for performance monitoring and how and so on?
So that it's not a performance monitoring tool, so it's not going to give you something, let's say a number that shows you how well your loop is behaving. But the only thing that it will do for you, if you have done your step testing, you have your model, you can of course judge how your current controller is behaving by using, let's say, the existing tuning here in the tuning case, and you can have a look at the tuning and see how that looks, if you're happy with that or not. So yeah. That's definitely a possibility.
Okay. Let's see what we have else. Okay, good. I think that is somewhat a summary of the questions. Yeah, some of the questions were pointing in the same direction, so I combined them into one. But anyway, so if you have more questions that pop up after the webinar, feel free to ask them. We will answer them by email and also send around to everybody the answer. So perhaps there are some questions that you forgot to ask, so feel free to ask them later on. So, okay, I would like to thank all the attendees to participate in the webinar. As I said before, we will send a link of the recorded session. So this session is recorded, the audio and the visual, the graphics. And I will send a link so that you can also distribute it to your colleagues later on, or if you want to look at it again because you missed here and there something, then you can do that. Yeah. And as I said, sorry, if you have any further questions, please send them to me. The next webinar will be after summer holiday. If you have suggestions on good topics, if it's about base layer optimization, software, advanced process control, maintenance of advanced process control, all these kind of things, then please let us know. Yeah. Also, when we close here the session, you will get a short questionnaire with some questions that you can also, what you thought about the webinar, what is not, and so on. So if you want to send me a longer email with your feedback also, please don't hesitate to do so. So again, Michiel, also many thanks for your time in preparing this webinar. So that's for now. Have a nice day to you all, and bye-bye.